This video is vector functions and space curves. And a vector function is also called a vector valued function, but we just call it a vector function. It is a vector whose components are functions, and the domain is the set of real numbers. So the notation is R of t equals a vector, and the first component is f of t, the second one is g of t, and the third one is h of t, similar to these parametric curves. Well, it's the same as these parametric curves we've been using. The other notation is f of ti plus g of tj plus h of t k. So these are the notations that we have, and I'm gonna do this video a little bit differently. You have to tell me if you like it. So the first thing we're going to look at is the domain. So the directions say find the domain of the vector function. I'm not going to write all that out. I'm going to say find the domain. And let's do an example. Let's say that R of t equals t to the third, the natural log of 3 minus t, and the square root of t. So as we look at this, let's take each of the pieces. So let's say f of t equals t to the third. And the domain of t to the third is all real numbers, which is negative infinity to positive infinity. The second function, g of t, is natural log of 3 minus t. And if you think about the domain there, so when we find domain, we say 3 minus t has to be greater than 0. So negative t is greater than negative 3, so t is less than 3. So our domain here is negative infinity to 3, not including 3, because you can't take the natural log of 0 or a negative number. So for h of t, we're going to say we were given the square root of t. So when we find the domain, that means we take the stuff inside the square root, set it greater than or equal to 0. That means that our domain then is bracket 0 to infinity. Now, in order to find the domain of r, the real valued function, what we need to do is find the intersection of the domains of the three components, because your domain has to be valid for all three of them. So if you take all three of these and intersect them, then the domain of r of t is 0 to 3. 0 to 3. I'm not going to work that out. I think that you're good with that, but you just needed to be reminded that you're going to look at the domains for all of them. So let's do another example. I like domains, so I think this is fun. Let's say that we have sine of t times which is sine of ti plus natural log of tj. They're going to throw a natural log in there because why not? Plus 1 over t minus 2. My minus and 2 ran together. So t minus 2k. So when we look at the I component, let's say the domain here is sines. The domain is all real numbers. When we look at the natural log component, the domain here is anything greater than 0. So we have 0 to infinity. When we look at the domain here, t cannot equal 2. T could be anything except 2, but you can't divide by 2. So we say negative infinity to 2, union 2 to infinity. So when we intersect these, the first one, the all real numbers, doesn't change anything. And then we have the intersection of 0 to infinity and this domain. Now the intersection for that is 2 to infinity. So the domain of r of t is 2 to infinity. Nice, simple, easy, as long as you remember domain. The next part of this lesson is about limits and continuity. I always say that Calc 3 is Calc 1 and Calc 2 in 3D spaces. So you're really going to see that happening. So we start off with if r of t equals the vector f of t, g of t, and h of t. Then this is going to make sense, but the limit as t approaches a of r of t equals the limit as t approaches a of f of t, the limit as t approaches a of g of t, and again, I don't have enough space, the limit as t approaches a of h of t, provided that each of the limits exists. Provided that each of the limit exists. Each component, provided the limits of each of the components exist. So if the limit doesn't exist, you have different problems here. So let's do a problem here. Okay, so this problem says to find the limit of r of t as t approaches 0. So that means that we're going to say the limit as t approaches 0 of r of t equals the limit as t approaches 0 of 1 plus t to the third I plus the limit as t approaches 0 of t e to the minus t j plus the limit as t approaches 0 sine t over t k. Make sure you have limit notation, that's important. So when you plug 0 in for t, right here you get 1 plus 0 I plus, we're going to plug 0 in here, and we have 0 times e to the 0, which is 1, j, plus the limit as t approaches 0. Now there's two things here. You can either memorize that sine t over t is 1, or I'm not very good at that, but I like L'Hopital's rule. So let's use, if we plug this in, we get 0 over 0, which is indeterminate form. To use L'Hopital's rule, you need a fraction, an indeterminate form, and a limit. So let's use L'Hopital's rule, and let's notate it right here, L'Hopital's rule. So that means we're not quite done with this problem. And when we take the derivative of the top, the derivative of sine is cosine of t, and the derivative of the bottom is 1 times k. Now I kept the limit notation because you have to keep the limit notation. We haven't finished it. So here we have I. This is 0. I'm going to write a 0 in for this minute. And then when I plug in 0 now, I get cosine of 1 is 1 over 1k. So this means our answer is I plus k. Now, if you have memorized that sine t over t, that the limit of sine t over t is 1, if you've memorized that the limit of sine t over t is 1, you could jump straight down to this green line, and that's okay. I don't memorize these things very well, but it only takes a second to use L'Hopital's rule and come up with it. So let's look at one more. It's number 4 in the book, and it says find the limit as t approaches 1, and they use this notation. They have t squared minus t over t minus 1 I plus the square root of t plus 8 j plus sine pi t over natural log of t k. Now you know the examples are never as good as never as interesting as the exercises. That's why I thought we'd do some of them. Let's take it piece by piece. Let's look at the limit as t approaches 1 of t squared minus t over t minus 1. So when we plug this in, we get 1 minus 1, which is 0 over 0, indeterminate form. Now, I love L'Hopital's rule, so I'm going to do this problem for you twice. We have the limit as t approaches 1 using L'Hopital's rule. So we get 2t, the derivative of the top and the bottom separately. So the derivative of the top is 2t minus 1, and the derivative of the bottom is 1, and 2 minus 1 is 1. Now, the second way to do this one is the limit as t approaches 1 is to factor. So if we pull a t out of the top, we have t minus 1 and a t minus 1 in the bottom. So then we have, this means we have the limit as t approaches 1 of t, which is 1. So you get 1 either way. You can pick. This one is my favorite. It uses L'Hopital's rule. as I draw a box right through the problem. Let me try to go over it. This is my favorite. The other one's the alternate. All right, now let's look at the second part. It says the limit as t approaches 1. You do need limit notation. Do not be sloppy. And this says t plus 8. Well, the first thing you do is plug and chug. So I get the square root of 9, which is 3. Good and done. And then let's look at the last one. It says the limit as t approaches 1. And we have sine of pi t over natural log of t. When we plug in 1, we have sine of pi, which is 0, and natural log of 1 is 0. So this one requires L'Hopital's rule. I cannot think of a different way for it to be done. So the derivative of sine of pi t is cosine of pi t. Chain rule, the derivative of pi t is pi. I'm going to stick that out front. And on the bottom, the derivative of the natural log of t is 1 over t. So now we're going to plug 1 in, and we have cosine of pi. We have pi times cosine of pi, which is negative 1 over 1, so we get negative pi. So our second component is 3, and our third component is negative pi. So that means we would write this answer as when you have the problem up here, then the answer is 1i plus 3j minus pi k. And hopefully that helps you out. A little bit of review of L'Hopital's rule and limits. It's been a while since we did limits. Well, we did them in Calc 2 in improper integrals and some in the series test, so hopefully it's not that old. A little bit about continuity. We say that a vector function R, or a vector function R, is continuous at A if the limit as t approaches A of R of t equals R of A. Now that kind of makes sense because our definition of continuous back in Calc 1 is a function is continuous if the value at that value equals the limit. So we're saying the same thing here. Now we can see that it's continuous if and only if all three pieces are continuous. So you can't be continuous at F and G, but not H. So all three pieces have to be continuous in order for you to have a continuous function, a continuous vector function. So we're going to work through these and moving right along. Next, we have space curves. This is not like outer space, but it's space curves. So if you look at this figure here, there's a connection between your vector function and your space curve. Suppose that f, g, and h are all continuous functions. So I'm looking at this function right here from the vector valued function r of t. So if they are all continuous real valued functions, then the set C of all points, where you have the parametric equations, because t varies, then you end up with this curve right here, and it's called a space curve. It's an interesting curve. Now we know the parametric equations to be x equals f of t, y equals g of t, and z equals h of t. So each of these parametric equations, as we were to plot the points, we call this a space curve. Now back in Calc 2, when we worked with these parametric equations, we called them parametric curves. But because we're living in 3D space, now they're called a space curve. And you can see this vector that goes to a specific point based on the point based upon what t is. So the equations right here, these equations here, are called parametric equations of C, and t is your parameter. And you can think of it as plotting the points and traveling through the space, and that's how we get our space curve. So then we're asked to describe our space curves, and that's where life gets a little interesting. Let's look at one of those. Notice the example says describe the curve defined by the vector function r of t equals 1 plus t, 2 plus 5t, and negative 1 plus 6t. Good news, we're asked to describe, not to sketch, so that's exciting. Let's write our parametric equations so we know that x equals 1 plus t, and y equals 2 plus 5t, and z equals negative 1 plus 6t. So based upon what we learned in chapter 12, we know then that we have a point in the normal vector. So our point would be the values 1, 2, -1. And the vector, let's call it A. The vector is 1, 5, and 6. So we know we have a point and a vector, and we know that this makes the vector equation of a line. This is the vector equation of a line. Remember that that formula is R equals R sub O plus VT or TV. And this up here definitely looks exactly like that. So we have a line. It's nice and simple. All we had to do was describe it. So we finished that one. This problem right here says to sketch a curve whose vector equation is the following. And it's in 2 space, so that's nice and pretty. So we're going to look at that. And in order to sketch a curve, this is a parametric curve. Remember that x equals t squared minus 3. We could get technical and call it x of t equals t squared minus 3. And then y of t equals t. So that's our parametric equation. So just like we did back when we learned parametric equations, here we have t squared minus 3, which is our x, and t, which is our y. And we need to pick t values. It's the vertex of this parabola in terms of t is 0, -3. So I'm going to pick -2, -1, 0, 1, and 2 for t. And then when I plug them into x, I get 4 minus 3 is 1, 1 minus 3 is -2, 0 minus 3 is -3, 1 minus 3 is -2, and 4 minus 3 is 1. And then for y value, we just have the t. And I don't know about you, but I get distracted by this. I'm going to take that out. And then we're going to come over here and graph these in a nice R2, our Cartesian coordinate system of x and y. So we have 1, -2. I guess I should just go ahead and fill in 1, 2, 3, 4, 5. All right, when x is -2, y is -1. When x is -3, y is 0. When x is -2, y is 1. And when x is 1, y is 2. So we have a nice pretty parabola, which is kind of what we were thinking it would be. But it's kind of easy to see if you draw those values. Let's look at another example. It still says sketch the curve whose vector equation is, and let's just put it right here. And let's say R of t equals, there's a couple in your homework. One of them is a line, so it's not too bad. But let's pick up one that it's not a line. So R of t equals 1t and 5 minus t squared. Now, this isn't too bad because we have 1 for a constant. So let's pick some values. Let's pick, WebAssign's going to give you some specific values to choose. But if I were graphing this just off of my head, I would go ahead and say that x of t equals 1, y of t equals t, and z of t equals 5 minus t squared. So I would draw a table. So I'm going to do it the way I would do it if I hadn't looked at what your WebAssign is asking you to do. So we're going to start with t, and then we have x, which is always going to be 1, so that's going to be easy. Y, which is going to be t, and z, which is going to be 5 minus t squared. So I'm going to pick -2, -1, 0, 1, and 2. There's no real method to this madness because its vertex is at 5 for the 501. So we have ones all the way down for x. Like I said, WebAssign gives you some very specific values to use. And then for y, we have -2, -1, 0, 1, and 2. I might not want to graph this many in 3D, just be prepared for that. So 5 minus 4 is 1, and 5 minus 1 is 4, and 5 minus 0 is 5, and 5 minus 1 is 4, and 5 minus 4 is 1. So we do have a parabola, and the x remains constant. So let me draw my 3D space here, and I'm going to kind of draw it out. not through the video, so I'm sorry you're not going to watch me draw it, but you'll see all my 3D drawings as it gets done. So I'm going to pause and draw this. Before I start to draw it, if we pick up these three right here, which are the center of the parabola, it's going to give us an idea of the graph. So I'm going to start with those three and then we'll look at it. This is the point 1, negative 1, 4. This is the point 105. This is the point 114. Now I could draw my parabola from here, but I'm going to go ahead and fill in the other 2 points just because. So then we can connect these points so we can see the parabola that's happening in 3 space based on this vector function, and it's not too bad. Let's look at one more. It says r of t equals cosine of, well, it's not vector notation, so r of t equals cosine of ti plus sine of t j plus tk. Now, when you look at these, we're going to start again with x of t equals cosine of t, y of t equals sine of t, and z of t equals t. And at some point, you can use these sometimes and others. So remember that x squared plus y squared equals 1, and cosine squared x plus sine squared x equals 1. Sine squared x, let's write the x in, equals 1. And that gives us a cylinder, and the cylinder that lies around z. So I'm going to pencil this in. So we have a cylinder with a radius of 1 around z. Now that's not what we really have because we also have that z equals t. So that gives us a different value here. So the sine and cosine give us this look right here. Whenever we have parametric equations of sine and cosine, it always makes a circle with a radius of 1. So we know that we have this cylinder here, and then we're going to trace it with z values. So if we used remember it's a radius of 1, so right here we have a radius of 1. Let's use a different color. So this is the point 1, 0, 0. And we can trace it around, and when you have 0 for z, it happens here. And then we also have, let's throw some points on here. We're going to use the fact that x squared plus y squared equals 1. So when we let t be 1, then z is 1. And let's start at 1, 0, because it starts here at this value on the circle that we talked about, 1, 0, 0. And then when t is pi over 2, then sine of pi over 2 is 1, and we have 0 for cosine. So it comes around to this point. It's not sitting on the y-axis here. This is the point 0, 1 pi over 2, and it's going to swing around the back because as the z increases, it moves up the circle. So that's why it's moving up the circle for the value of z, and it's traveling around this path of the circle, and it comes around to the front like this, and it makes a dotted path, and it comes around to the front like this. So this creates the helix. This is the helix, which is a spiral that looks like this. And you're used to hearing about the double helix from science. So the DNA double helix, and that happens in coiled springs. And so it kind of comes from something similar here. This gives us our one side of that double helix, but it gives us our helix. This problem says to find a vector equation in the parametric equations for the line segment that joins the point P, 132, to the point Q, 2, negative 1, 3. Remember that to find the equation of the line, you need a point, so we have one here. And you need a vector, so let's find the vector between the point PQ. And so we have 2 minus 1 is 1, negative 1 minus 3 is negative 4, and 3 plus 2 is 5. Now we know this gives us the line r equals the the first value is 1 plus 1t. The second value is 3 minus 4t. And the third component, let's use component, not value. And the third component is negative 2 plus 5t. That gives us our line between P and Q, but we're asked for a line segment. So think about, where does this start? Well, when T equals 0, this is where it starts at P, because if you plug 0 in for T, you get each of those values. And if we plug 1 in for T, then we're going to get the ending at Q. Let's check that. If we put 1 in for T, 1 plus 1 is 2, the Q value. 3 minus 4 is negative 1, which is the y value of Q, and negative 2 plus 5 is the t value of Q. So it works out that way. So we can say that the line segment that joins the 2 points are, as we mentioned above, R is 1 plus t, 3 minus 4t, and negative 2 plus 5t. And then in order for it to be a line segment, we're going to define it when t is between 0 and 1. And that gives us our line segment. It's not too bad of an example there. Let's look at another one. This example says, find a vector function that represents the curve of intersection of the cylinder and the plane. So think about your cylinder. We have a right circular cylinder that we've talked about before that goes around Z and has a radius of 1. And the plane y plus z equals 2. I'm not going to ask you to draw one of these. I'm going to bring in a picture for you. You can think about the fact that we have a right circular cylinder and a sheet of paper that cuts it. So we're going to kind of have an ellipse. So here you can see the intersection of the two. And on the figure 5 on the left-hand side, we have a really pretty intersection. And on the right, you can see the points of intersection that help you form the ellipse that rotates around it. So since x squared plus y squared equals 1, then we know that x has to be cosine of t. So x equals cosine of t, and y equals sine of t, and then z equals 2 minus y. That's how we can use it to find our points of intersection of the two. But the corresponding vector would be r equals cosine t I sine t. Now we can't say 2 minus y because y has a value. So let's go ahead and make that 2 minus sine t. So our vector r is cosine of t, sine of t, and 2 minus sine of t. Let's shrink this in just a little bit. 2 minus sine of t. So you can find the vector equation, and then you can find t values when t is 0. When t is 0, then cosine of 0 is 1, sine of 0 is 0, and 2 minus 0 is 2. So that's how we got this point here, and we can find the other points accordingly. It's not too bad of a problem when you stop and think about this x squared plus y squared equals 1 as these two parametric equations. And that's an interest, it's pulled in a lot, it's used a lot. So this right here, this vector r, is called the parametrization of the curve of C. So you can see, and because it's a parametric curve, we do have arrows. See the arrows pointing around? I highlighted one of them for you. All right, so then the question is, what else do you have to be able to do with this? Okay, so this problem says, find the equation of the plane that contains the curve with the given vector equation. And the problem said, this example is r of t equals 3 sine t, cosine t, and negative cosine t. So what we're looking at is we're looking at the ones that kind of go together. And let's say that x equals 3 sine t, y equals cosine t, and z equals negative cosine t. So if you look at these two here, we can say that z, since y equals cosine t, we can use that down here and say that z equals negative y. And this is a plane because it contains two of them. So that is the plane that contains the given equation. Let's do another example. And it says the same directions, find the plane that contains the curve with the given equation. And let's say r of t equals 4t, and in this one we have sine of t, and in the third component we have t plus 8. So we could say x equals 4t, y equals sine of t, and z equals t plus 8. Now x equals 4t is really good for us here, but I don't want to play with fractions. I'm going to solve this one for t. I'm going to leave the sign alone. I have to tie two of them together to get a plane. So we're going to say t equals z minus 8. Let me say that again. You need two of the variables to be linked in order to get a plane. So you need two variables here. And since I now have t equals z minus 8, I can put that in for x and say x equals 4t. So x equals 4 times z minus 8. So x equals 4z minus 32. So that is the plane that links those two. And that's not too bad of a problem there. It's kind of nice, kind of easy. Let's look at another different set of examples. At what points does the curve given to us here, this vector curve, intersect the paraboloid z equals x squared plus y squared? So if you think about what's happening here, let's look at the top, and our parametric equations are x equals t, y equals 0, and z equals 3t minus t squared. So let's plug that into our paraboloid, and we're going to say z, which is 3t minus t squared, equals x squared, which will be t squared plus 0. So if we bring this to the other side, we get 3t minus 2t squared equals 0. So we're going to factor to solve. So we get t times 3 minus 2t equals 0. So t equals 0, and 3 equals 2t, so t equals 3 halves. So then when t equals 0, we're going to plug that into our r of t. Then we are asked to find what points do they exist. So we're looking for points. So the x point is 0, the y point is always 0, and the z is 0, 0, 0, so 0. Now when t equals 3 halves, when we plug that into our parametric equations, x is 3 halves, y is 0, and z would be 3 times 3 halves, which is 9 halves, minus 3 halves squared, which is 9 fourths. So that gives me 9/4. So these are the 2 points where the vector curve intersects the paraboloid. Now the next one says, at what point does the helix intersect the square? This one's a little bit different because we have our trigonometry happening here, but it's still not bad. Let's start with our parametric equations. X equals sine of t, y equals cosine of t, and z equals just t. Now if we plug those in here, we get sine squared t plus cosine squared t plus z is t squared equals 17. And sine squared plus cosine squared is 1. So then t squared equals 16. So t equals plus and minus 4. That means that we have 2 sets of points here. We have t equals -4 and t equals +4. We're in radians when we do this problem. So we're going to take sine of -4 to be, let me punch it in my calculator here. Sine of -4 is positive 0.757. The directions said to go to 3 decimal places. So we have positive 0.757. And then cosine of 4 is, the cosine of -4 is negative 0.653. And then z is -4. And then when t is +4, the sine is negative 0.757. The cosine is again negative 0.653. And t is +4. Z is t, which is +4. So these are the 2 points of intersection. I guess the direction should say at what points there are 2, where the helix intersects the sphere. But if you think about a sphere, it's a nice 3D circle, so the helix is going to cross it probably more than once. Definitely more than once. We have the points of intersection. So let's look at one more thing before we wrap up this lesson. Using computers to draw space curves. Now, Desmos is beta testing 3D drawing, so you could play in Desmos. But if we look at this, it says space curves are inherently more difficult to draw by hand than plane curves. For an accurate representation, you need technology. For example, figure 7 down here. This one shows a toroidal spiral, and it's called such because it lies on a torus. Another interesting curve, the knot down here, comes from these parametric equations above. Neither of these curves are easy to draw by hand, but even when they're drawn by a computer, it's hard to get a really good idea of what it looks like. So if you look at example 7, it says use a computer to draw this. You can play with it in Desmos. There may be another way to do it. Figure it out, play with it, or just look at the sheets on the screen. It's all good. I'm not going to ask you to do this because I'm going to ask you to do things by hand on your test. So let's look at what this graph looks like. So all of these figures represent the example 7 that we looked at on the previous screen. And it said R of t equals t squared, t cubed, and it's called a twisted cubic. So you can see this is the looking down the flat version. And all 6 of these here represent the twisted cubic from different angles. So it says you can get a better idea if you look at it from different viewpoints, so that you kind of have an idea of what it is and why it's called a twisted cubic. So that makes perfect sense now. Sometimes it's easier to see it when you draw it on a surface. That's what this sentence right here is saying. So take the twisted cubic in example 7 and look at it on a parabolic cylinder. And figure 10 below shows the cylinder and the twisted cubic, and you can see that it moves upward from the origin. So this 3D picture right here helps you get a better example of that twisted cubic. A third method for looking at this is to look at it on the cylinder, x equals y to the third, so you can see this here. Now, the book website has visualizations, so you can look at them there. And some computer algebra systems right here give you a clearest picture by putting it in a tube. So I can let you read all this. You can pause it and read it. I'm not going to, but so if you find some computers that help you do 3D drawing, it'll help you get an idea of what it looks like. And down at the bottom here are details concerning the physics involved and the animations of trajectories. You can check those out. And I hope that you learned something and enjoyed this lesson. Have a great day.